This is the golden age of astronomy. And tonight, the astronomers want to share their excitement with us at a rare moment of discovery such as may never occur again. And to help guide us among the new discoveries around the world of the astronomers and through this vast universe, we have with us Carl Sagan from Cornell University.
Our sun is a star. It seems large because it's so close, but for all that, it's a humdrum and quite ordinary star. We've modeled the sun and the nearby stars. Here, this star that's blinking is our sun. Near it are the neighboring stars in space. Because of our vantage point near the sun, we're able to recognize the familiar constellations of the night sky. To the north, we can see the Big Dipper, pointing towards the pole star. Near the Milky Way, we can see the familiar winter constellation Orion. If you live in the southern hemisphere, you'll recognize the Southern Cross. Let's take a stroll among the stars. Let's amble north. As we do so, let's keep an eye on the Big Dipper. Notice how its shape seems to change as our perspective changes. The reason is that the Big Dipper is composed of stars, some of them intrinsically bright, but rather far away, some dimmer, but closer in. The constellations that seem to be points of light painted on the vault of the heavens are really composed of stars at a variety of distances. And if there are creatures that live on planets of other stars, they will see different constellations in the night skies than we do. Well, we've reached a star which astronomers call Gamma Cephei. It's so far from the sun that it takes light some 50 years to travel from the one to the other. The earliest signals of our technical civilization on the Earth are only just now reaching Gamma Cephei. These signals are the earliest radio broadcasts, perhaps an aria of Enrico Caruso, but we do not know if there's anyone here to listen. Let's take a look back the way we've come. Let's try to see if we can recognize where we've come from. Which of these stars is the sun? The sun is such an insignificant star that we can't make out which of all these stars it is. In fact, the only way we can do that is to ask it to blink for us. Blink, sun. There it is. We can now amble back towards home. As we do so, we can recall that these points of light in the sky, every one of them is as mighty a star as our sun. Let's head home to our familiar solar system. As we do so, we can recognize the planets accompanying the sun. Looming up is the giant planet Jupiter, a gassy planet very different from the rocky and metallic Earth. As we move inwards from Jupiter towards the sun, we can make out the red planet Mars, a possible abode of life, the target of 2 American space vehicles now on their way to explore Mars. If we continue further inwards towards the sun, rapidly passing by our home planet, we reach Venus, a cloud-covered planet with a searing hot surface. At the present time, there are 2 space vehicles launched by the Soviet Union, which are headed towards Venus, perhaps to land there. Let's now return to our comfortable and cozy home planet, the Earth, with its tiny moon which circles it.
This is the year of Apollo, when men may first set foot on the moon. It's an extraordinary enterprise, a first step into the universe. But distances in the universe are so vast that they're often reckoned by the time light takes to cover them, at 186,000 miles a second. The moon is a little more than 1 light second away, and light from the sun takes 8 minutes to get here.
In our little excursion among the stars, we traveled a total equivalent distance of perhaps 100 light years. Later on in this program, we'll be concerned with immensely greater distances of billions of light years. Compare that with the tiny 1 1/3 light seconds between the Earth and the moon. Astronomers worry about two very large questions. How does the universe work, and where did it come from? In this program, we consider both these questions on the nature and the origin of the universe. The first question is an attempt at understanding what we see in the sky in terms of known natural laws. Why does the sun shine? How do stars evolve? What's the explanation for these extraordinary cosmic explosions which astronomers are detecting with appalling regularity? The second question is an even deeper one. Is it possible that the universe was made instantaneously from nothing at some remote epoch in the past? This is the view taught by Babylonian astronomers, and it's familiar to us from Genesis 1:1. Its modern astronomical version is called the Big Bang theory. Or is it possible that the universe had no beginning, that it's infinitely old, as some Oriental religions teach? One modern astronomical version of this theory is called the steady state theory. We consider both these theories later in the program. We begin with the forces of nature and how they work in the stars. We'll encounter three principal forces. The force of gravity, which holds stars together and keeps their insides hot. Nuclear forces, which produce starlight in the insides of hot stars. And magnetism, which in a way is the least potent of these forces. And yet, look at this soaring, awesome surge of hot gas rising some tens of thousands of miles above the sun, guided by the sun's gravity, by the sun's magnetism. In this picture, this tiny circle represents the size of the Earth. It's to scale. In a way, it's a lucky thing that we're not this close to the sun. To further examine such disturbances on the sun, we go first to a unique observatory in Australia.
At Kalgoorlie, in the outback of New South Wales, a remarkable new telescope watches the sun. 96 dishes deployed in a 6-mile circle operate as one huge instrument, collecting the radio noise that tells of the violent explosions on the sun.
This is a cluster, 10 billion years, twice the sun. Some of them are colored red and have enormous dimensions. They're called, for this reason, red giants. When our own sun is about the same age, it will have exhausted much of its available nuclear fuel in its interior, and it also will become a red giant. Its outer layers will expand, it'll become distorted, extended. It will engulf first Mercury, then Venus, and eventually our own planet, the Earth. Our oceans will boil, our atmosphere will dissipate to space, and it's interesting to ponder whether our remote descendants, if any, will be equal to the supreme challenges of such times. But fortunately, this is all several billions of years in the future. Red giants blow their outer atmospheres off into space, forming a kind of cosmic smoke ring, like this. The remainder of the star then collapses, contracting to form an extraordinary kind of object called a white dwarf. Actually, red giants and white dwarfs are part of contemporary astronomy and not something from the Brothers Grimm, as it might sound. A white dwarf is something so dense that a teaspoonful of it would weigh a ton. The initial energy of gravitational collapse heats the star, so it's white, but it has no other fuel supplies to draw upon, and it gradually cools, ending up its days as a cold, black, dead ember, little bigger than the Earth. Massive hot stars have a much more dramatic and much briefer life than the sun's. But let's begin by considering the biography of our sun, starting some 5 billion years ago, when it formed out of the mother gas between the stars. Release of gravitational energy makes the star gradually hotter as the material falls in.
But that capital of energy does not last very long. The reserves of nuclear energy do not come into play until at the very center, hydrogen begins to react, or burn, as we say loosely, to make helium. Its radiation is produced at the center and wanders to the surface. This is how the sun is now, halfway through its active life. But eventually, it will run out of fuel. At the center, it will begin to burn hydrogen further out and swell into a red giant. Then, the center becomes hot enough for helium to react. The star is burning its ashes. It suddenly readjusts itself before starting to grow again. In this phase, the sun will swallow the Earth. It's short of fuel now. The surface layers are then blown off to form what we call a planetary nebula. But the rest of the star contracts to form a very small and hot white dwarf. Burnt out, with no energy supply left, it simply cools down. After billions of years, it simply becomes a pile of dead ashes. Now, let's consider a more massive star. Let's say a star 15 times more massive than the sun. It begins its life roughly the same as our sun does, using gravitational energy to heat its interior. But gravity keeps its insides much hotter. It expands itself 60 times faster than the sun does. And as we'll see, it eventually gets hot enough to make much fuller use of the possible nuclear fuels. The immense heat released originally by collapse under gravity is quite quickly radiated throughout the star. The surface becomes very hot. The star eventually begins burning hydrogen in a large core for most of the star's lifetime. But when hydrogen fuel runs short, nuclear burning of heavier elements begins. First helium, forming carbon and oxygen, which are also burnt. Then neon, magnesium, silicon, eventually forming iron, which can't burn in nuclear reactions. The core suddenly cools, collapses, and a supernova is produced. The outer body of the star is racked by a nuclear explosion and blasted into space. Astronomers have long thought that what is left at the end of such a nuclear explosion is a white dwarf, that very dense star we talked about before, with a density of a ton per teaspoonful. You may think that's dense enough. But it now appears that what may be left at the end of such an explosion is not a white dwarf at all, but a neutron star. A star with the incredible density of an atomic nucleus. It's, in a way, the world's largest atom. It's so dense that an equivalent density would be if you had compressed the Earth into a size about 100 yards across.
At Arecibo, the pulsar work is led by Frank Drake.
Observing pulsars is like listening to a Beethoven symphony. There is the rhythm of the pulses themselves, and within the pulses, a complicated pattern of notes, sometimes at one frequency, sometimes at another, just as in the melody of a musical composition. All of this gives us clues as to what the pulsars are. Certainly, they are very small stars, stars that have collapsed under their own gravitational pull to tremendous densities.
6 months ago, no one could connect the pulsars with any other object in the sky. The break came with this radio telescope, the Mills Cross of Sydney University, sited at Molonglo near Canberra. The antenna arms are a mile long.
Let's see roughly why Schmidt was so shocked and what his spectrum meant. Imagine a bright source of light which is moving rapidly away from you. The light waves that it emits are stretched out. They're moved towards longer and therefore redder wavelengths. The faster the thing is moving away from you, the more red-shifted its spectral lines become. Astronomers are by now used to the conclusion that with the biggest reds, that is those which are moving fastest away from us, also the most distant galaxies. It turned out the faster a galaxy is receding from us,
the swifter, the more distant it is. Now, with this information, it's possible to show roughly what Schmidt found. Schmidt's quasar spectrum is this middle spectrum. The upper and lower spectra are comparison laboratory spectra. Schmidt recognized a pattern of 3 lines due to atomic hydrogen. But these 3 lines were not in their usual place in the spectrum. Their usual place is somewhere over here. They had been redshifted by this very large distance. The amount of the redshift corresponds to a velocity of about 30,000 miles per second. And such an enormous velocity means that the quasar must be very far away. In fact, that it must be about 1 billion light years from the Earth. Now, how is it possible that an object which appears to us so bright could be so far away? A huge mass of gas or stars falling together might conceivably produce such a large amount of energy, enough to drive a quasar. But there's a problem with this idea. It's that gravity is, in a sense, too strong. There's nothing to stop the collapse of such a mass of gas or stars. It would continue to collapse. It would pass through the neutron star stage that we talked about before, and eventually its gravity would become so intense that even light would be unable to escape from the object. Therefore, the object would turn off. It would disappear. It would vanish from the universe, leaving behind only a sort of black hole of gravity, a little like the grin on the Cheshire Cat. The universe may, in fact, be riddled with such black holes. Imagine a spaceship wandering around, minding its own business, encountering such a black hole. What happens to it? Well, it must vanish. It must disappear from the universe. There are some who believe that matter which disappears down such a black hole must reemerge at some other point in space, at some other epoch in time. This may be just a sort of highbrow science fiction, or it may really be true. The quasars are such a puzzling phenomenon that they may really lead us to revise our notion of the laws of nature. It wouldn't be the first time that astronomy has taught physicists something new. But it does seem clear that simple common sense notions about the universe are just totally inadequate to account for such an extraordinary phenomenon as a quasar. We should keep an eye on this part of the Milky Way towards the center of our galaxy. Some strange things are happening there. Not only is it a source of gamma rays, but it's also an intense source of infrared radiation, as these contour maps imply. Dutch radio astronomers have found clouds of gas rushing outwards at high speed from the center of our galaxy. They imply that there was a violent event, an explosion at the center of our galaxy some 30 million years ago. It wasn't an explosion as violent as in a quasar. If it had been, we wouldn't be here today. It was just a sort of tremor. Scientists narrowed down the mystery of creation. All that seems to be necessary is some gas at the beginning. And how hydrogen condenses into a furnace of stars, how these stars cook heavier elements in their interiors, how these heavy elements are spewed out in supernova and other explosions to enrich the interstellar medium, and how subsequent generations of stars and planets form from the hydrogen and heavier elements. If in the laboratory we duplicate a primitive planetary atmosphere and supply it with some energy, what is produced are organic molecules quite like the ones which make us up. It's an extraordinary thing. It's as if the origin of life is in the cards, as if it's a forced process of physics and chemistry. And we understand, at least in principle, how from these humble beginnings, life could evolve to produce wondering men who ponder how it all came about. And we must not think that we are the pinnacle of creation, the end product of cosmic evolution. It may well be that Elsewhere, there are creatures more advanced than we. While there is some uncertainty about many of the steps in this grand picture, the overall pattern is agreed to by most scientists. And yet, there's the beguiling problem: where did the original hydrogen come from? We've talked about exploding stars and exploding galaxies. In the Big Bang theory, we're living in an exploding universe. In the Big Bang theory, the universe began some 10 billion years ago. It was instantaneously created. All the matter and energy in it were produced somehow from nothing. As the primeval gas cloud expanded and cooled, there were condensations in it, condensations which evolved to produce galaxies, not all of them spirals. The subsequent evolution in the Big Bang theory takes many forms. In some of them, the galaxies expand from each other forever. In others, they slow down and contract, and there's a sequence of Big Bangs. In the Big Bang theory, there's no mystery about the recession of the galaxies. It's no more mysterious than the expansion of the fragments of a bomb explosion. In the steady-state hypothesis, the universe has no beginning and no end and no outer boundary. There's no quarrel in Hoyle's view with the expansion of the universe. Galaxies recede to a distant horizon, but their place is taken with other galaxies newly formed from the intergalactic gas. As more and more generations of galaxies are produced, perhaps you think that the intergalactic gas should be used up. This is not the case, because in the steady-state theory, new gas is produced all the time from nothing. And how is it produced? It's produced in just the same way that in the Big Bang theory, matter is made from nothing.